So what is our third problem?
Well, the issue is that we didn't have this when we were just dealing with that ginormous table. But once we shrunk this table, it became possible that we could have two keys, like this, A, C, B, D. And this isn't necessarily going to be true in the real world implementation, but for example, let's assume that the hash function A, B, C, D, and A, C, B, D, they produce the same value. Okay, let's suppose that A, B, C, D produces the value when it's thrown into the hash function 13, right? And A, B, C, D, and A, C, B, D. So H of A, B, C, D produces 13. And then H of A, B, A, C, B, D also produces 13. Now, let's assume that we put foo with A, B, C, D in first, right? So 11 mod, so 13 mod 11, that gives us index 2. So we'll put foo there. And suppose we wanted to put ACBD and bar in. Well, we'll get ACBD, and that hashes to the exact same space, and we end up trying to put bar into an index that's already occupied by something. This is what we call a collision, right? And collisions occur where, because our table size is small, well, small in comparison to the infinite size of all possible keys, so two things may want to occupy the same slot in a hash table. And this is perfectly fine, we just have to come up with a way to resolve that. Now the two ways we're going to learn to resolve that are actually fairly straightforward. The first is called open addressing, which just simply means that, okay, I wanted to put foo here, and I also wanted to put bar there, right? Their keys said they end up in the same index. So the way we deal with that is that we look for the next available space and put bar in the next available space, right? And if we want to put bars here, well, we get a collision here again at index 2, well, we go on to index 3, oh, that's also occupied, go on to the next one, and we put that there. Right, we just look for the next available space. That sounds stupid, again, but it works. It's actually really good and really efficient. The other solution is called chaining, or using buckets. And rather than using an array of just these values or these entries, as you'll see, instead what we use is that each one of these, and I'll actually just draw 5 here because that's easier to draw. Each one of these slots in the array, it's not an array of entries, it's an array of linked lists. So this will be, so we start out with, 5 null linked lists here. And when we insert our first item, let's say foo maps to index 2, right, we'll create a linked list where the head of it has foo in it. And then when we want to insert bar, there's a collision, well, we just simply tack it to the end of the linked list there. And then once it grows to a certain size, we resize it. So let's review our problems. Problem is that we needed to take in a key, and we were using a giant array, okay? And we need to take in a key and convert that into an index so we can sort in our giant array. And our solution was, well, keys can be anything, so we just turned it back into an integer because everything's just numbers anyway at the very end of the day, okay? Problem 2. I don't want to waste 4 gigabytes with a giant array. So solution, use a small array, and to make sure that everything, so we don't get an out of bounds error, we just simply mod everything by the table size. This led us to problem 3, which is that we can now since we're dealing with a table that's smaller than infinity, we can end up with 2 keys wanting to end up in the same finite amount of space. They want to occupy the same small amount of space. So we need to, and that's called a collision. So problem 3, dealing with collisions. How do we deal with collisions? One was open addressing, which is that we just simply use the strategy, if my space is occupied, go to the next available space. If that's occupied, go on until there's an empty space. And the way we will this is so that we'll always guarantee there's always an open space. And then the then the other way to do that was chaining, which is rather than holding a single item in any single linked list, we instead of holding a single item in any slot in the array, we instead let each slot of the array be a linked list. And as we insert items into it, if there's collisions, we simply will allow them to just add an item to the linked list if there's a collision. So this gets into why we want to make a good hash table, or hashing function for our hash table. If we make a bad hashing function, like if my hashing function is that given a key, the value is always going to be, given a key, your index is always going to be 2, right? If my hashing function was that, then everything is just going to simply end up here, and all we end up is, well, we're wasting a lot of space to produce a linked list. And now our lookup time is not constant because we're actually just using a linked list. Similarly, if I was using open addressing, then basically everything gets a collision on index 2, so we occupy this space, then we occupy this space, then we occupy this space, then this space, and so on and so forth, until we fill it up and resize, and then everything. We just go on the same vein, and so it just becomes adding to the end of a linked list where we don't have a tail runtime. So it just becomes O of n time as well. And that's not good either. So a good hashing function will distribute things evenly throughout the table. And again, we leave that to the hash code function to deal with that. So that's all we need to get started with building a hash table.